Go.
Okay, okay. Yeah,
Okay.
it should be fine, huh? Okay, thank you. Okay, then I will start. Thanks a lot, Salvatore. And again, I'm sorry for these technical issues. This is the disadvantage not being physically in your very nicely building to present this topic. So in this advanced, let's say, technologies for hydrological modeling, I will present the topic about soil plant digital twin, and this is sounds like a buzzword, but then actually we are really trying to use this as kind of a technology to push our boundary for the development of land surface model for understanding, for example, drought response of ecosystems. So together with Professor Bob Su, we are currently really, let's say, harnessing our efforts into this direction, and then with the contributions from the following students and postdocs. So Yunfei Wang, who is the PhD student right now, he's actually doing his second PhD with us. The first one is in China. And then he coupled STEMU, which is a soil model, with a scope, the vegetation model, and the long list for FluxNet sites. So FluxNet is kind of a flux tower site. So Salvatore, because I don't see audience, so in case there's any questions, please feel free to stop me, huh?
Okay.
And to be interactive.
Sure.
Okay. Um, And then we also have Zhengjing Sum, who is covering plant hydraulics. So I will also introduce this briefly. And then with the Dangyang Yu, we also incorporate the plant growth model. So this I will explain why. The plant growth model means we have also the dry matter for stem, for root, for leaf, and all this kind of crop growth part can be simulated as well. At the same time, we are considering carbon and nutrient dynamics. And all these four parts, let's say, are process-based studies. And then when you run this process-based model, is quite heavy. And we also use machine learning-based approach to build emulator of this process-based model. And then we also use satellite data, for example, upscale from the point, let's say, plot scale to regional or even global scale. At the same time, we also couple this soil plant system with a groundwater model, which is model flow 6. And then to do all this, we also need support for high performance computing. And we have a colleague from East Science Center doing this. Oh, can you hear me now?
Yes. Now, yes.
Okay, because you were calling me from WeChat. Oh, what's up? Okay.
Yes.
No,
Because we
okay. So now it's okay. Um, yeah, I need to pay attention to this microphone then. Okay, so this is the structure of the slides, and in the coming slides, I mean, I will see how although I prepared a little bit too much slide, but then the idea is really to put everything there, then you can also refer back later on, and we will see where we can pause, and then we take some time for the practice. Okay, so I will yes. Any?
Okay, good.
Okay, so I will introduce briefly the motivation. So why we want to do this? So one of the motivation is really about optimizing the soil water conditions for crop growth. And in the right plot, I think you can see my mouse. So it's kind of a typical landscape in the Netherlands. And then you have a farm, you have a village, you have river and the streams. So most of the time in a farm, you will see something, some instruments like this, which is kind of a water pump. Yeah, and for the let's say water irrigation, water management in the Netherlands is actually quite straightforward, because most of the time it is a very wet place, and I mean particularly for this year, it's 3 times wetter than usual. So they use this water pump a lot, and this is how you. Therefore, you see, yeah, there are a distribution of this water pump across the country. So the management is very straightforward. When there's too much water, you just pumping water out of the field, and then if there's too little water, then you irrigate. So this works usually very efficiently in the Netherlands. However, although you don't see it this year, but then like last year and 2018, there are consecutive, let's say, drought event. Yeah, it's continuously very dry periods in the past several years, and then that creates problem because when it is very dry, the let's say ENV, so which is a Ministry for Infrastructure and Water Management, they will issue certain kind of a ban on irrigation. So farmer cannot use the water to do the irrigation anymore. And on top of that, I mean, the drinking water company, of course, I mean, the drinking water is the priority to maintain. So the drinking water company will continue to extract water, groundwater, for drinking purpose. Then because of this ban of irrigation and the continuous extraction of groundwater, then this will give even, let's say, a bigger problem for the agriculture sector. So basically, in the past, in those dry years, the agriculture or food, let's say, sector in the Netherlands are suffering the loss. And not long ago, or several years ago, LTO Netherlands, LTO means is a kind of a farmer organization in the Netherlands. They initiate or establish a legal framework for compensation for drought damage. So the idea is they trying to identify the impact of drought on their agricultural production, and then based on this part of a damage estimation, they can apply for some compensation. Yeah, but if you do this individually, it is very time consuming. So basically, what they are trying to do is to using the National Hydrological Model, which is called LHM, in the Netherlands, to simulate, yeah, where the agriculture fields are suffering drought damage. So, for example, based on this National Hydrological Model simulation, you can identify some yellow regions, and those regions are suffering, let's say, drought damage. And then they can ask farmers in that region saying, hey, do you want to apply for this compensation for drought damage? And then this is actually, you may ask how much it will cost for this damage compensation. Huh? So this is 30 million per year, 30 million euros per year for the drinking water company to pay for the farmers. And then now it suddenly became very important to understand what's the accuracy of this model simulation. Yeah. So this is the NH and let's say National Hydrological Model Simulation, and all the compensation for the drought damage are based on this model simulation. Then you may ask, how accurate this model can represent the drought damage in my field. Yeah, if it is overestimation, farmers are happy, but the drinking water company are not happy. On the other way around, right? So, so this became very important to understand this model simulation and its accuracy. So this is from kind of hydrological model point of view and from farmer point of view. And then there's also another motivation is from ecosystem point of view. So we had a let's say long-term flux observation site in the Netherlands, which is a Spiegelbos flux station. And here we observe like water, energy, and the carbon fluxes. So during 2019, I just used this time series from 2019, but equally you can find it, from 2018, 2020, or 2021. So here is just example for the July 24 to 26 of 2019. You can see that the air temperature reaches above 35 degrees. So this is a very critical temperature limit for ecosystem to stop photosynthesis. And this has consequence. So as we see here, for I'm not sure if you you can see the bottom right. Is there anything blocking your view? Oh, you are muted. Okay, it's fine. I think it should be fine. Huh? I just keep the floating window on my bottom right. So I hope that is not blocking this slide. In any case, so here I just want to say, okay, for the 24 to 26 of July, you have this very high air temperature. And then you can see the evapotranspiration are, let's say, are still very high for these 3 days. However, for the net ecosystem exchange, meaning if you have a carbon, if it is positive, then it is carbon uptake. If it is negative, meaning there is a carbon emission. So, or respiration of the ecosystem. So according to these 3 days, although the evapotranspiration remain high, but then the carbon uptake is kind of diminished. And then during the nighttime, you can see there's a very big respiration compared to other days. And this is not compensated, which means during these 3 very hot days, the forest actually turned from a carbon sink to a carbon source. And then this is a question we need to pay attention. If consider in the past consecutive dry years or very, very hot periods, and then also let's say for the climate projection, it suggests the drought events will become more frequent. Then we really have a good reason to worry about this. Yeah, if the forest really turned from a sink into a source, then the 1.5 degree, let's say, target will be very difficult to achieve. Okay. Let me see. Because now I don't see this window. Okay, yeah. Okay, so of course you may argue. From the drought period, the drought impact in terms of the carbon uptake, is not easy to be visualized. Yeah, because it is measured by the eddy covariance system. But then if you go to, let's say, a nature reserve or reserved or kind of a natural park in the Twente region where my university is located, then you can see there are some very shallow lake just disappeared. So, for example, in the left part, it is kind of indicating, let's say, this is a kind of everything in the Netherlands is somehow constructed, although it is called a nature park or things like that. But then in the left figure, you can see there's a shallow lake and it's working very fine and looks beautiful. But then in 2022, it is actually drying up. So this also gives you some kind of a visualization of the drought impact. So based on those motivations and the let's say the impact of the drought, then we're trying to do something. I mean, starting from 2018, and then we apply for this project. It's called Wonder, and it is trying to understand the water use and drought response of the agriculture and the nature ecosystem in the Netherlands. So we have 19 partners. This is a kind of a national fund. And we have 6 university, let's say, partners or knowledge institutes. And then we also have co-funders, for example, from companies like Fundasat, which is purchased by Planet. And also we have HKV is kind of hydrological, let's say, company, yeah, on this hydrological modeling and also monitoring. We also have government organizations, water boards, private companies, as I mentioned before, but also the farmer associations, because we want to build the connection with our stakeholders. So the aim is really trying to address this drought impact, and the primary, let's say, purpose of Wonder project is trying to create integrated system for monitoring, modeling, and predicting drought and response of these soil plant systems. And then with this soil plant digital twin, we're trying to also develop some scenarios and options for managing or planning the agro ecosystems, and also to meet, let's say, to adapt to this drought impact, and then of course do some training and capacity building. And then to do this, of course, we have several hypotheses. So this is of course based on the let's say current situation in the Netherlands. For example, if you look at the right plot here, you can see one plot is very green, the other plot is very yellow, and this is during the 2018 drought event. And such kind of a contrast between wet and dried will create this advection effect for the calculating of, let's say, for the calculation of evapotranspiration. So this is a so-called advection effect. And then we want to quantify this. Secondly, well, this is the second hypothesis, but then the first hypothesis is that current the NHI models, so the model I referred to before, which is used to calculate the drought damage, is using reference evaporation. Yeah, but then we know the reference evaporation, I mean, it's not actual evaporation. It's most of the time much higher than the actual evaporation. So then you may argue, okay, what's the impact of changing this use of reference evaporation to actual evaporation in these NHI models? And then you may get a maybe more accurate estimate of the drought impact. Yeah, so we also trying to do that and collaborating with NHI community, so National Hydrological Instrument model. There's also diversified diversity effects, which means, I mean, if you look at the right figure here, there's a forest. This is called so-called agroforest, but it's also called food forest. And like within this forest, they have different species. They have high trees, they have low, let's say, berry trees and things like that. And the benefit of having such a kind of a biodiversity is that you have also quite a diverse rooting system. Yeah. So for those trees, you have a much deeper rooting system which can tap into groundwater. For those shallow shrub, then you only have very shallow rooting system. Then, I mean, during the very dry period, the shallow rooting system will suffering for, let's say, lack of or very low soil moisture availability. However, during those very dry period, the deep rooting system we are able to extract water from the groundwater and then distribute it to the shallow layer. So this diversity in above ground species, but also because of this diversity of different plants and the trees, they also have a diversity in the rooting system, and this rooting system is helping with each other. So during the dry period, yeah, the much deeper rooting system will take water from the groundwater and then distribute it to the shallow layer and helping those thrive with a shallow rooting system. So this is of course, I mean, our hypothesis, and also farmers they see such a kind of diversity effects, but then you still need to use the model and also using the in situ monitoring network to see if indeed you can see such a kind of effects. There are also other hypotheses. So in terms of the water availability and crop water needs, and this is linked to soil plant digital twin part. So I will come back to this later. But in general, in the right part, it just gives you an overall structure of the Wonder project, what we are trying to do. So there are part links to, for example, monitoring, measuring, but also modeling and the satellite observations. And all this, we're trying to quantify the soil plant system in an accurate manner. And then we talk to stakeholders like farmer associations, and at the same time, we also using this, how to say, the process-based understanding, and then use this information, soil plant system information. We provide inputs for the socio-economic models, so we can also evaluate socio-economic impact. So in the coming slides, I will just briefly introduce different science and the measurements we have been doing. So as mentioned, this project is really focused on understanding the drought impacts in the Netherlands. So we have several sites. Yeah, one in Twente. So this is where we are based in the University of Twente. And then also Salvatore has been here. We also measured several other ecosystems in the center of the Netherlands and also in the south of the Netherlands. So this is just to show you some fieldwork photos. So this is me, and this is Bob Su, and this is our colleagues, Murat. And then we also have Lidwin, who are digging ditches to bury this land surface, how to call DTS, distributed temperature sensors. And the idea is to have integrated monitoring of the evapotranspiration, energy balance, but also soil moisture, soil temperature profiles to understand the response of the whole system to drought events. This is another site. It's a food soil boss, so it's a food forest. This food forest is nearby our university, so we can go there more frequently, and therefore we also put a little bit more observation sites there. We also measure another food forest a little bit far, but then in this Kettlebrook food forest, we have two sites. So one is located within the food forest, the other is in the surrounding fields. So as such, you can see the contrast. In total, we actually sampled more than 120 soil samples. So we want to determine like a soil bark density, porosity, soil texture, and all that kind of soil properties. But we also have 11 stations for soil moisture, soil temperature profiles. And then we installed 5 metal so-called Atmos stations, is measuring 12 metal variables. And then we have 3 eddy covalence or energy balance stations and water potential measurement in the soil, but also in the plant. And this DTS system, as I mentioned, distributed temperature sensing, And then we also have a scintillometer to measure the evapotranspiration. And we also conduct greenhouse experiments to understand water stress and the nutrient stress on photosynthesis. So in the coming slides, I will briefly introduce example of a food forest being, let's say, being climate resilient during the 2018 drought. But then after that, we put up two stations, one in the food forest, the other in the, let's say, surrounding sites. And then you can see there's a really a big contrast. One is a very browning because of the drought impact, and the other even impacted by drought, but still looks green. Yeah, but we know, we know. I mean, intuitively, forest will be more drought resilience, but then we want to quantify it with the data and the model simulation. Okay, so one hypothesis why the food forest is more resilient is because they have this fancy underground network, which is established by different mycorrhizals. I will not go details into different, let's say, mycorrhizals, but just to say, okay, with forest, with quite a biodiversity, you have, let's say, very interconnected, let's say, network underground, which increase or let's say improve the water holding capacity, but also increased the carbon sequestration. And this is actually our data. So as I mentioned, we installed two locations. One in the right is in the food forest. One in the left is in the surrounding fields. And then we take soil sample as well. And then we monitor the soil moisture and the soil temperature profiles. And then if we look at the top figure in the left here, then you can see the saturated water content in the food forest is much larger than the surrounding field, which is raygrass. So raygrass is grown by the traditional farmer, and they harvest it for using machinery and for let's say horses. Yeah. So, but you can see that, I mean, since in the forest soil has higher, let's say, porosity and than the surrounding field, and at the same time, you can see that the bark density is much lower, yeah, than the raygrass. So the blue line are forest, these yellow lines are grass field, and you can see, I mean, this. The forest soil has higher saturated water content at the different layers, and also at the different layers, you can see the bark density is much lower in the food forest. So the bark density lower means the soil is less compact. Yeah. So if the soil is less compact, then it creates more buffer to hold water content, to hold, let's say, soil water. And this can be seen also from the Luzon soil moisture curve. So this is a grassland, this is a food forest, and then we can see that the difference between the lowest moisture content in the grassland to the highest water content in the grassland is actually quite limited. It's between, for example, 0.22 to 0.35, let's say. Then you have like a water holding capacity like 0.13. But if you look at the food forest, yeah, this can go very, let's say, dry to 0.13 or so. And then you have a 0.35, which means you have like 0.22. This range of water can be captured by the food forest soil. So which means the food forest has larger water holding capacity than the grassland. And this is although intuitively learned, I mean, by our experience, but then this is also can be seen now using the data. So this is just for, let's say, water holding capacity. But if you look at the Luzon soil temperature, then you can see also the grassland is much hotter than the food forest soil. Yeah, so this is now you can see it from the data as well. Or this is just to show you, let's say, because of the drought event, the food forest is also became a focus of the news media. And then I was interviewed by a national newspaper last year because of this project. We are monitoring the effect or resilience of the food forest, and which just to let you know, let's say the Dutch let's say society, they pay also a lot of attention to the food forest and also this drought impact. So this is just kind of a conceptual diagram to say, okay, in order to understand the drought response of the food forest, we want to monitor the water balance, yeah, and at the same time also energy balance and the fluxes of the food forest. And with those data, we also establish this so-called soil plant digital twin based on, for example, a user interface with a Jupyter notebook. And this is actually the part I trying to do practical with you, but then because of the shared account cannot be opened in an efficient manner, so we will skip it. But then all the codes, all the source codes and data are available on GitHub. So I will give you the link later on, and then you can check it out by yourself when you come back to the recorded lecture. So maybe briefly, I already tapped into the concept of soil plant digital twin. So why we call it a digital twin? If we look at the process, so basically the water will be uptake by the plant through the root water uptake, yeah, and then this water will go through the stem and then go to the leaf, and then join this photosynthesis processes, and then you have carbon uptake. You also have this solar-induced fluorescence. So all these are actually kind of a signal can be sensed by the satellite. Yeah, and all this signal, or let's say Earth observation of the soil plant system, can be feedback into a model through the data simulation, and then the model can improve the prediction of the soil plant system, and then feedback the information like, okay, when you should already start the irrigation, and when you need to drain the field, or when you should store water for the coming dry period. So the soil plant digital twin is really a concept trying to utilizing the model, utilizing the satellite observation, in situ observation, and then harness them into information dashboard to provide operational advice for the farmers to do irrigation water management, to do some kind of local measures. Okay, so I talk about this digital twin, yeah. So and actually, this digital twin Earth, this whole concept is actually populated just a few years back, and then we know several years back at the EU level, they initiate this Destination Earth, let's say, program, and this is kind of flagship program. It is called Destiny. It aims to build a very accurate digital model of the Earth and to simulate and also to monitor the natural, let's say, ecosystem, and also the interaction between the natural ecosystem with the human activities. And then as such, to anticipate the extreme events and trying to invent some adaptation measures to address these climate related challenges. So this is actually part of the Green Deal. I'm not sure if you can hear, you have the audio. I will try to play so I will try to play a small video But let me know if you are able to hear the sound. Can you?
No, we can't hear the sound.
Oh, you cannot hear the sound. Okay, okay. Then I will skip this part. The idea is
we can see the images. We can see the images.
Yeah, it's okay. You can watch it later from the shared PowerPoint. Is also okay. Yeah. So actually, I trying to use that small clip video to introduce what's the concept of a digital twin, and then link it to the concept of digital twin Earth. So I think you may heard about this digital twin concept before or from somewhere, and basically it said digital twin is kind of a digital representation or replica of a product or processes, and using the real-time sensor data and algorithm. Yeah. So the digital replica of the product and the process need to be established using the real-time sensor data and an algorithm. And then when you have this digital twin, then you can virtually simulate basically everything that will happen in the physical world. Wow, maybe everything is a little bit exaggerated, but the idea is really to simulate everything. So it's to push the boundary, yeah. And then because the digital twin can virtually simulate everything, so it provide insights for future planning and also the product development. So this allows us to test and also to better understanding the quality of the products in early stage. And this will minimize the downtime and also reducing the cost for product development. Yeah, so this is the idea of the digital twin. So this is from the industry, from the aviation industry, from all the car industry, or from whatever industry, let's say requires such kind of a digital twin. And the concept is invented from there. So people apply it to also the earth science. And how this is applied is actually very straightforward. So we can say the real world data from across Earth, for example, from the satellite, from in situ networks, they are, how to say, the real time sensor data of our Earth. Yeah. And we know we also have this Earth system model or dynamic models of Earth system. Then we can say, okay, Earth system model is the algorithm. So as such, with this Earth system model and also the satellite data, in situ data, then we basically can simulate the past, the present, and also the future of our Earth. Yeah. So this is easy to understand. For the past and the present, for the past, let's say it's something like era 5 reanalysis. Yeah, reanalysis data from ECMWF. And for the present, it's something like nowcasting. Yeah, so when you have the Earth observation data, and then you can predict the numerically the weather conditions. And then for the future, of course, it depends on what you define for future. You have a medium range weather forecast, which is in coming 2 weeks, and but then there's also climate projections, yeah, based on different scenarios. So with this Earth system model or digital twin Earth, we can simulate the past, the present, and also the future. And then if we can accurately predict the future, then we are able to prevent, for example, not prevent, but at least to reduce the damage. Yeah, can be caused by extreme weather or caused by whatever hurricane and other extreme events. So the idea of this digital twin Earth, very importantly, is two parts. So you have kind of a virtual space, which is called the digital twin. Yeah, so it can be a digital twin Earth, but it can be also a digital twin of a soil plant system. And then very important part is this data. So we really need real-time data, and which can be incorporated into this digital twin or virtual space, and then which will provide information like a forecast, like a prediction of extreme events back to the real world or real space, and then we can do some adaptation measures, and then all this will change the system, and this kind of change to the system will change the soil plant states, and which will be sent by the satellites, by the in situ data, and then which feedback again to the numerical model, and then so forth and so forth. So you have such kind of data information cycle between the physical space or real space and the digital twin, the virtual space. Yeah. And actually this concept is actually, yeah, let's say the data assimilation. And then maybe you heard about data assimilation also from somewhere, but here just a very brief diagram to show the power of the data assimilation. So the orange curve are observation from satellite. For example, we can say, okay, this is a kind of cloud structure as observed by the satellite, and here is Aqua Modis and the CloudSat radar. Yeah, you can monitor the cloud structure in a 3D dimension, and then you know where there's a rain event and where there's just cloudy and things like that. And then the green curve are model. So you can I'm sorry, the green curves are observation, yeah, and the orange one are model. So as you can see, those black dots and also let's say are kind of satellite images, yeah, and then we can see the original model are not capturing these three black dots in a nice way, but then after the data assimilation, then this green curve means refined, let's say, model simulation, which is also called analysis. And then this model simulation line now is much more closer to the three observation points. Yeah. So compared to the orange one, let's say the top curve, orange one here, you can see the green ones are now much closer to the observation. And this gives you a better estimate of the initial condition, and then which will increase your accuracy for prediction. Yeah. So this is the idea of assimilating the observation, and therefore this data assimilation is really the core for this digital twin engine. So with that, then I may also briefly introduce the current digital twin engine, or let's say digital twin Earth, is established by ECMWF. So they have basically 6 components. You have a high performance computing, and then also data handling. So this is mainly links to big data processing or handling. And then there's a simulation, observation, fusion. This is called data assimilation as well. And then, as I mentioned before, the machine learning is really needed because the process-based modeling is very time-consuming and expensive. And now ECMWF are also embracing the machine learning more and more. They lately just released Alpha AI fast. So it's kind of artificial intelligence IFAS. IFAS means integrated forecast system. And then they also have a complex process optimization. So means, I mean, when you have a very complex workflow and also very complex codes, how to optimize the workflow to make it running more efficiently. And then you also need to have a standardized data digital twin interface. This means this will come very convenient for the community to, since how to say, to be more effectively to synthesize the efforts from different groups when you standardize this digital twin interface, because when you develop, let's say, I will come maybe next slide is easier. So if you look at the list slide, it's actually people are calling for making more digital twins. Yeah, so although we have one Earth, but you can have many digital twin of Earth for different perspective. So for example, you can have a digital twin on weather-induced and geophysical ink strings. You can also have a digital twin on climate change adaptation, because it depends on which part you are simulating the Earth system. And then you can also have a digital twin for biodiversity and digital twin for oceans. Then the question comes, I mean, how to link up all these different digital twins together? Then a standardized digital twin interface is very much needed to link up and to couple all these different digital twins together. Yeah, so that is why we needed this. Let me see. Yeah, that is why we needed this standardized digital twin interface. Okay. So with that as kind of a background, and that is why we want to develop a digital twin for soil plant system. And as I mentioned, you need basically three components. One is the process-based model to replace, or not replace, but then really to represent the soil plant digital twin in the virtual space. So-called a digital replica of the soil plant system. And then also we need a kind of machine learning algorithm, and I call it physics aware machine learning, or physics informed machine learning. Is mainly trying to incorporating our physical, let's say, knowledge on the process into this machine learning algorithm to build emulator. And this will enable us to compute more efficiently the model at a much larger scale and for many sites. So I will come back to this again later. And then also, as I mentioned, data simulation is very important as one component of the digital twin concept, because this allows us to incorporate near real-time data in terms of satellite data or in situ data. This is another project we dedicated for developing this soil plant digital twin. So although it is not a very big project like Wonder, but then we do have many people involved. So you have someone in charge of this process development, or overseeing the development of different processes, because as I introduced at the beginning, there are different components of the soil plant system need to be developed. And then we also have high performance computing facility supported by eScience Center. We also have this cloud platform. Unfortunately, this cloud platform capacity is not, let's say, working fine nowadays, and is under maintenance. So therefore, we can have a shared account to play with all of you. But then we can come back to that later. I'm still asking for creating this shared account. So when it is ready, I will send it to you all, and then you can all have try after I show, let's say, the steps, and also using the open source code. So now I will go a little bit into details, technical details in terms of the process understanding of this soil plant system. So we built this soil plant digital twin using, let's say, this STEMUscope model. And what the STEMUscope stands for, it stands for vegetation part and also soil part. For the vegetation part, we use a scope model. And the laser scope model can simulate photosynthesis, can simulate energy balance, and also radiative transfer processes at the leaf level, but also canopy level. And at the same time, it can simulate the reflectance and also the fluorescence. So you simulate straightforwardly the satellite signal. And in the soil part, we have the stimulus model can simulate soil water content, soil temperature. So you can also simulate this dynamic root growth, and correspondingly, you have this dynamic root water uptake. And all this will help to construct a soil plumb hydraulic resistance scheme. Yeah. And as such, you link the soil plumb system with the satellite data. A brief history of the STEMUScope model. We basically developed a STEMUS soil model already back to 2011, and then it's till 2020. It is coupled with a STEMUScope model. And then further, we have InFit1 to couple the let's say different components of the scope model to the STEMUS model. And then for the scope vegetation model itself is also back to 2004 already, and then it's TL 2020. Then we couple the STEMUS and the scope model together. So we're not going into too much details there. This is again a small video clip introducing the soil plumb digital twin and how to model them. I will skip this part, and then but the link will be provided in the PowerPoint, so you will be able to watch it later on. It's a very short one, 6 minutes or so. I will skip. How to wait a minute. I think I need to. Can I go to next slides?
Eugene,
Yes.
we can share. If you share the link, we can play it from here.
It's okay. We can play later. We can play later.
We play it at the end of the presentation.
Yes, I want to play the presentation, but then somehow I think I need to. Okay, let me stop sharing and then I share again. And then this one. Okay. And then I will share one more time. Yes, those links are in the PowerPoint, so we can, I think it's okay to do this after the lecture. Yeah. Okay, so in the video, I basically just introduce quickly why we want to build a soil plumb digital twin. So basically, like what I introduced before, and this is a kind of a technical digital infrastructure, how to enable such kind of platform. And you basically need 3 parts. So we have a model input, and then using this model input, you provide, you process the data, and then you provide it to the model or the emulator, and then you can get the output, which can be utilized to analyze the drought response, for example. Okay, so let me see. What time is it now? So Salvatore, I mean, in the coming slides, it's all technical, and in terms of the model development and it is performance. I can go through them as well quickly, but let me see, what time is it now? We can also try to, let's say,
we have time. We have still some time, so you can go on for another 15 minutes, let's say, even half an hour if you need, and then you can move to. We will have a break. Okay.
So okay, so like a 15, let's say 15 minutes more, and then let's do a break, and then we can also break now. I mean, as you wish, and then we can do some demo. I mean, it's up to you.
I think it's better to split the two part of the lecture, the theory first and the demo later.
Okay, then I will finish it in 15 minutes about the theory, and then I will go to the demo.
Okay.
Yeah.
Then we take a break and then we go for the demo. Okay.
Yeah. Okay. Yeah, that sounds okay. Okay, let me continue then. So I was introducing this model, STEMUscope, soil plant digital twin. Then we also want to evaluate the performance of this model. For example, in terms of understanding the drought response. And this is one of the sites we used. This is a FluxNet site from the United States. It's a grassland site. And then from the data, the black dots here, you can see that, I mean, after day 120 or so, there is a kind of a water stress, or 110. But then the top row is using the vegetation model only, so without considering the soil model. So if you recall the previous slide, I was introducing this soil plant system and then also the soil plant digital twin using the soil model and the vegetation model. And now I just use the vegetation model to simulate this ecosystem like a grassland in terms of GPP and evapotranspiration. And then you can see, without considering the soil model, the vegetation model is overestimating the GPP and the ET dramatically. And now if we're using this STEMUscope model, which is coupled soil and the vegetation model, then you can see the GPP and the ET are simulated in a reasonable manner. Yeah, they are in a good agreement. And after this, then we upscale it to 170 sites of the FluxNet site. So this is the distribution of the FluxNet site. So when we upscale it to FluxNet, there's a problem. So using STEMUscope model, I mean, using a relatively high-end laptop, we need to spend 1.5 hours for 1 month simulation period. So if we translate this computational cost to run 170 sites, then it is about more than 3 years. Yeah. So it's a 1,150 days or so. Because the 170 sites is 1,532 site years. So this is a lot of data to simulate. And then using this original version of the STEMUscope, then it takes more than 3 years to finish. And then if we want to run it globally, it's even more ridiculous. So therefore, we after this building this soil plant digital twin with the help from eScience Center, we reduce the computational cost dramatically from several years to 5 days. But this is still not fast enough. And then we build an emulator, which is currently already developed, and we can run, for example, for Pan Europe, for 7 flux variables, but also including the SIF, which is solar-induced fluorescence, 1 hour, 9 kilometer in 15 minutes. So that is more decent. But that is also the idea why we need such a kind of a soil plant digital twin. Well, this is again rather technical in terms of the input data, what do we need. So like a solar, let's say solar wave radiation, long wave radiation, metal variables, but also plant parameters, runoff parameters, and the soil parameters. And then going through this STEMUscope model, then you can get the ecosystem, water, energy, and the carbon fluxes, but also soil state variables and the fluorescence, even the leaf water potential, which I will come back in later slides. So we evaluate also the performance of this STEMscope for running this 170 sites in general, in terms of simulating net radiation, latent heat flux, sensible heat, ground heat, GPP, NEE, and also soil moisture and soil temperature. They all performed in a good, let's say, manner, in a reasonable manner. One thing I want to highlight here is that, I mean, when we run this STEMscope model for 170 sites, we didn't tune the model. We just use the global available data. So like MODIS LAI, ERO5 data, some existing soil hydraulic parameters, and also soil grid data. And it's already reasonable matching the in situ data, so we are quite happy. But still there are some issues. So we also evaluate the model performance in terms of different levels of soil wetness. So, for example, for the wet, for the mild situation, for dried situation, or for the very severe dried situation, and then we can see for the normal and also for the wet situation or for the dry situation, the model performed relatively well in terms of latent heat flux and the GPP simulation. But then for the severe dry situation, there's still some problem. And this could be due to the hydraulic resistance scheme we, let's say, utilized in the STEMscope model. So this is the hydraulic resistance scheme I referred to. So currently, we use these three parameters, and using this Ohm's law. So you have this resistance, and then you have the water potential gradient. Then you can calculate the root water uptake, which is equal to the transpiration. Nevertheless, this is still kind of a resistance scheme, and it's not kind of explicit Planck hydraulic pathway. And what do I mean by the explicit Planck hydraulic pathway? So this is basically, for example, if you look at the left column, left diagram here, when you have the water, it will enter the root to the stem, to the leaf, and then you need basically the hydraulic conductivity within the root, within the stem, within the leaf, in order to capture this Planck hydraulic pathway, or let's say Planck hydraulic flux. So we also did that in our model. The idea is actually very straightforward. It's just applying the Darcy's law into the soil plant system. So as long as you know the water potential gradient and you know the hydraulic conductivity between soil and the plant, within the stem, on the leaf, then you can calculate the water fluxes within the soil plant system. So we used in situ site in China to do the validation, just to check if the model works or not. And then it turns out working okay. Maybe it's not very obvious for net radiation, sensible heat, and the ground heat, but then for the latent heat flux and let's say carbon fluxes, it performs relatively well and also improved, because in the first row is a STEMscope model, the original version. The second row is the Planck hydraulics version. And then you can see there's some improvement in terms of, although it's not a very significant improvement, but still, the latent heat and carbon fluxes are estimated much better. We can also look at this the time series. So you can see the red curve are the Planck hydraulics version, the blue curves are original model, and then you can see that the Planck hydraulics version improved the estimation of latent heat flux and also the GPP quite a lot. Another thing is that with this Planck hydraulics version, now we can simulate the water potential in the soil, in the root, in the stem, and the leaf individually. And then you can plot the diurnal variation of all these water potential variations. And then you can see that during daytime, let's say the leaf water potential is the let's say the largest in terms of the suction, yeah, and then in the soil is let's say the lowest. As such, you have this upward water potential gradient, which enable the root water uptake. So meaning at the leaf, stem and the root, they are much more drier than in the soil, which enable the root to extract water from the soil. So this is during daytime. So this is understandable, right? You have during daytime, you have very strong root water uptake, supply water for the transpiration. However, during the nighttime, then you can see that the soil water potential and the leaf water potential are in equilibrium. So meaning, I mean, during nighttime, it recovered a bit. It reached the equilibrium, like you don't have the root water uptake during nighttime. And that is also reasonable, right? During nighttime, you don't expect too much transpiration, too much root water uptake. Okay, so let us the plant hydraulics part, and then as I mentioned before, the STEMscope can link this process to the satellite signal. So for example, for the solar-induced fluorescence, we can simulate the SIF spectrum, we can simulate the reflectance, also the irradiance spectra, and all these satellite signals are actually linked to photosynthesis, links to also the whole soil plant system. And we most of the time people actually tends to how to say using the SIF and the GPP as kind of very direct relationship. And this left plot here actually showing this apparent linear relationship between solar-induced fluorescence and the tower-based GPP data. And you can see they indeed are linearly correlated. However, this is only under certain hypothesis or assumption. So for example, if there's no water stress, then you can see such kind of a linear relationship. So currently in the community, most of people think, okay, the fluorescence is linearly correlated with GPP, but actually it is not. And in the right panel is the simulation result from STEMscope, and we can also simulate this linear relationship. But at the same time, if you pay attention to the green and the red dots here, they are nonlinear. And this is because for the linear relationship, we give the system enough water, yeah, to supply for the transpiration. So there's no water stress. When there's no water stress, you can see such kind of a linear relationship. But if it is during the dry conditions or drought events, then you can see such kind of a nonlinear relationship. On the other hand, if you look at the fluorescence signal with leaf water potential, you can find a linear relationship. And this is mainly because the fact, let's say within the STEMscope model, the water stress factor, which is a function of the root soil moisture content and also the root length flexion, are controlling the leaf water potential. And because of this, let's say, link between this root soil water content and leaf water content and leaf water potential, so there's this kind of hydraulic connection within the soil plant system. And such kind of a hydraulic connection enable this kind of apparent relationship between solar-induced fluorescence and leaf water potential. I will leave this, I mean, this could be a little bit too much specific in terms of a process understanding, but in any case, I will leave these slides here, and then you can also, if you have some questions, please feel free to write me email. So we also measured this because the water potential is a very important variable. So we also measured this water potential in our sites using this so-called microtentiometer. So in the coming slides, I will just go relatively fast. I think we are approaching the break. again, this slide is, I mean, from the previous slide, I tried to express, let's say, the soil plant system is very, how to say, hydraulically connected with each other. Yeah, so this kind of a soil plant hydraulics regulating the whole system, and then it also regulating the satellite signal like solar-induced fluorescence. And this diagram is just give you a more detailed process understanding in terms of such kind of soil plant hydraulic connection, but also this soil plant hydraulic connection to the satellite signal. In the coming slide, we also incorporate this plant growth into the STEMscope model, and the idea is that currently we need to use LOAI as input for STEMscope, but we know the LOAI data is not always there, and then when there's no LOAI data, then you cannot run the STEMscope. However, if you can simulate the plant growth, then you can simulate LOAI as kind of a state variable. So for facilitating that, we also incorporating the plant growth into our model. As such, you can simulate LOAI dynamically, and then you can run STEMscope for forecast purpose to do the prediction. And this is just kind of a simulation result to show you, let's say, we can simulate LOAI, and when it compared to MODIS, it also show quite a let's say, reasonable agreement with each other. And then we also can simulate the dry matter of different components, like a dry matter of root, dry matter of leaf, and also the dry matter of stem. But then we can also compare with the LOAI. And the one thing here, actually, I want to highlight is that because of this simulation, you can see, I mean, from satellite data, sometimes you can have kind of uncertainty. For example, for the beginning of the growth period, you can see this kind of a sharp increase of LOAI, and this could be due to the uncertainty of the satellite data. And if you take this satellite measured LOAI into the model, then you can also have unrealistic simulation of the GPP. But then if you use the plant growth module, which can give you much smooth, let's say, development of LOAI in the beginning of the growing season, then you don't see such a kind of jump of GPP in your simulation. Yeah, so this also kind of advantage to have this plant growth model. Another thing we incorporate into the model is to consider the canopy structure, because currently the LOAI is evenly distributed to the whole tree in terms of the whole plant height. But then we know, I mean, a plant or tree has a canopy structure, and then we're trying to incorporate this canopy structure into STEMscope. And then in order to do that, we use LO system. And so currently this LO system structure has been incorporated into the STEMscope as well. But the paper is not yet out. We are preparing it to submit it in the near future. So this is using another site. We are validating our improved version in terms of a simulation of carbon, water, and energy fluxes. But all these are currently under development and will be, let's say, submitted soon. In the coming slides, I just some kind of notes. I just trying to say, okay, yeah, there are some kind of technology can have very high resolution scanning of the leaf structure. So, for example, we can scan the leaf structure in a very high details in terms of substomatal cavity can be visualized. We can visualize the vascular bundle. We can also see chloroplast and all kind of things. So which means we can create a virtual leaf, because this is linked to the soil plant. Digital twin, you can call this is a leaf a digital twin for leaf. Yeah, and this is structure. But I mentioned the importance of the leaf water potential, and people start to invent also very innovative technology to measure the leaf water potential as well, like hydrogel, like inject gel into the leaf in order to monitor the leaf water potential and then to understand where the evaporation occurs within the leaf. People are using 2D model to simulate water potential and the temperature of the leaf, and this can help you to identify what's the place you can have this evaporation within the leaf. So imagine the leaf is very small, and you're trying to understand where the evaporation takes place. You can also use in 3D to do that. So the question, comes. Is more detailed, and the detailed processes are developed every day. So are we going to include all these very detailed processes into the land surface model? The question could be yes and no, but it depends on what's the purpose of the soil plant digital twin you are aiming for. And there is also such kind of editorial paper like a Think Big and a Model Small. The idea is saying, okay, you have very detailed processes to consider, but then you need to incorporate all these small processes in order to simulate that kind of processes. But if you don't have these small processes, then you cannot say, okay, it is not important. Yeah. So in order to say important or not, we need to incorporate that kind of processes. Okay, Salvatore, I think I will stop here, and then the code, let's say the open source code is here. Yeah, so feel free to take a picture, or you can scan also later on after break, and then I will start to have some quick demo. Is actually quite a simple. I will just explain briefly the workflow, and then when I have the shared accounts, I will send the email to everyone, and you can repeat what I'm going to do after the break. Yeah.